thank you for joining today in the morning with a different schedule as compared to the normal afternoon sessions of the BC seminars. Today I will present Pablo Zarco, that is a full professor at the University of Melbourne, but he's also an associate scientist at the Institute for Sustainable Agriculture in Cordoba, and a good friend and a good collaborator. So Pablo will talk today about the modeling, imaging spectroscopy for biotic and abiotic stress detection. And remember, after Pablo's presentation, you can make any question using the chat. For those that have problems, maybe you can use the speaker, but please preferably use the chat and type your questions. So Pablo, the floor is yours. You have about 30 minutes.
Okay, thank you very much, Blanca. Thank you, Blanca, Giuseppe, and Leonardo for inviting me to talk about modeling and a bit of remote sensing in the context of Xylella, but also talking about other pathogens and the induced symptoms. For the audience with no expertise or experience in imaging spectroscopy and remote sensing, I always like to show this video. It shows a plane and how data are collected. And at the same time it's collected, you can see on the right-hand side here, you can see the full spectrum that is being recorded. Basically, what we do with imaging spectroscopy is basically the same thing that we normally did, or we normally do in a laboratory, where we apply spectroscopic methods to collect data in several spectral bands, but we do it on a plane, or we do it on board a drone or on a satellite. That is what is called imaging spectroscopy, or also known as hyperspectral remote sensing. And what we do is scanning the surface with linear array sensors or other type of multispectral sensors co-aligned with a number of spectral bands. And I'll get into that in a minute. And because of that method and that technology, what we normally get is hundreds, sometimes thousands of spectral bands, usually between 100 to 300 spectral bands. But sometimes, like for example, here in our lab, we have an imaging spectrometer with more than 1,000 spectral bands, very, very narrow in specific spectral regions. And again, for people who know about remote sensing, this is probably not needed, but just to put it in context, when we collect data with our cell phone, we get the three basic spectral bands, blue, green, and red. If we use multispectral cameras, then what we get is a number of spectral bands, 5, 6, 7, maybe 10, 12. That is usually the maximum number of spectral bands at specific spectral regions. If instead of multispectral, we collect several bands covering the full spectrum, then that is what is called hyperspectral imaging or imaging spectroscopy. And if we click on an image, hyperspectral image, like this one, if instead of hyperspectral, what we get is multispectral, then that is what we will get. It's a number of spectral bands in the specific regions. This is what we normally get with satellite sensors that we have, or we collect the number of spectral bands which are discrete and at a specific wavelengths. If instead of multispectral sensors, what we get is what we fly or what we collect or what we use for collecting data is a hyperspectral sensor or an imaging spectrometer, then that is what we will get. We get the full spectral signature, that is called. If we did that, if we collect so many different spectral bands, because here what you see is the full signature, and that full signature, what is really made up is of hundreds of spectral bands within the first and the last spectral region at which the sensor is sensitive. Because we have so many spectral bands, we can evaluate the effects of different physiological processes or different traits or different things happening to vegetation. So here you can see that is coming from modeling. We can see the effects of, for example, leaf structure on the full spectrum. And we can see the regions, the spectral regions where the changes occur or the major changes are happening. If we look at the photosynthetic pigments, chlorophyll, carotenoids, anthocyanins, xanthophyls, then we see that they absorb and they major changes are happening in the visible part of the spectrum. Why? Well, because that's the region where the light is absorbed for photosynthesis, as we all know. And the same thing for other traits like water content, dry matter content, and whatever we are interested in. Because we can collect so many spectral bands, the traditional method that we have been using for assessing vegetation, I'm talking now in general, biotic or abiotic stress, lack of water, nutrients, growth, links with yields, I mean, whatever we are doing with remote sensing for crops or vegetation monitoring can be done, or what has been proposed to be done using what is called vegetation indices. And there's a large number of those indices available. And in fact, this is very old in some ways. I can show you here one of the very first paper in the 70s, more than 50 years ago, in which it was proposed a reflectance ratio. I mean, the ratio between two spectral bands, calculate different reflectance data using this handheld radiometer related to, for example, in that case, in that particular paper with green biomass. So again, this was proposed many, many years ago, more than 50 years ago. And there's a family of spectral indices or vegetation indices that can be used. And it's very easy in some way to use them. They are related to all those things that I said before. Those indices are related to, for example, structural changes. Well, growth, canopy density, leaf angle distribution, all these aspects affect those indices, and they are designed and developed specifically for tracking structural changes. Chlorophyll, not only chlorophyll A and B, but carotenoids, xanthophyll, anthocyanins, wherever photosynthetic or non-photosynthetic pigment absorbing radiation can be, in principle, detected and we can design a specific index to track it. Water content, photochemistry, photochemical constituents, and photosynthetic dynamics and changes. So in principle, it's quite easy, and that is the first attempt to monitor vegetation has been done since the 80s, I would say, using vegetation indices that we calculate from these type of images, being those images hyperspectral or multispectral. As long as they have sufficient spectral bands, then we can calculate on a tree-by-tree basis, like we can see there, we can calculate, for example, NDVI, which is one of the most widely used indices. Or we can use any of the other indices that have been proposed, which are related to, for example, chlorosis, because of the reduction of chlorophyll concentration or nutrient deficiencies or so on. It's straightforward, and it's in principle easy to do it because we just need a number of spectral bands to do it. So one of the first attempts that we tried was as part of the PhD thesis of Rocío Calderón that was co-supervised with Juan Antonio Navas in Córdoba. And we already demonstrated at that time, those papers are coming from about 10 years ago, that there are a number of spectral indices or vegetation indices like the ones you see here that are sensitive to the severity. That is in the context of verticillium wilt in olive. And those results already demonstrated that we could get overall accuracies of around 70 to 80% accuracy. And that was good news because in some way, with ratios or indices, depending on which ones they were, and depending on where they were calculated, we could detect the disease or the symptoms induced by the pathogen. And that allow us to evaluate or to do something that we call a screening of vegetation indices, which are sensitive to the severity. And this other chart is in the context of Xylella fastidiosa. And that was one of the first papers that where we demonstrated that some of these indices are in fact sensitive to different levels of severity. And those are photosynthetic pigments, also indices calculated to track chlorophyll fluorescence, coral water stress index calculated from thermal, that's not from hyperspectral data, or other structural indicators or indices. And they would be sensitive more or less depending on the severity levels. But the overall summary is that we already got at that time over accuracies of around 80%. And kappa coefficients that were quite satisfactory in terms of levels of false positives and false negatives that we would obtain. So the question then is, are vegetation indices all we need to detect biotic-induced stress? And the reason I'm discussing about it is because I thought was a good opportunity to discuss and to talk about the modeling aspects that are needed when we are trying to do obtain models which have good performance across different scales and also species. The fact is that indices are very easy to calculate. We just need an image with a few spectral bands, and we can calculate ratios or normalized indices in a very straightforward. So that is the main reason why indices are so widely used in remote sensing. There are hundreds of indices available, as many as combination of different bands that we could calculate from the images. Even from cameras which are 5, 6, 7 spectral bands only, we can calculate a number of indices just by calculating all possible combinations of bands. And they are available from both hyperspectral and multispectral. We don't need hyperspectral or more advanced technologies. With simple multispectral cameras, we can calculate those indices. And that's why they are, again, very widely used. And we have, the entire scientific community has demonstrated that they are very well related to vegetation traits. They are proxies that work generally well. If we are interested on detecting the symptoms or the effects of pathogens, but as well, if we are interested on monitoring, for example, nutrient deficiencies or lack of water, inducing water stress, or any other changes in growth. But the problem is that what is the actual meaning of vegetation indices? What is the meaning? If we know that NDVI is 0.7, what does it mean? They don't have physical units. So they are normalized or non-normalized ratios, and they are not referring to anything based on the actual physics of the radiation vegetation interactions. How stable they are. If we calculate indices in one, or we collect an image in one particular site, and we calculate indices, a bunch of indices, a set of indices, how stable they are if we come back again to the same place, for example, or if we go to the orchard which is nearby. And how transferable are models built with those indices? I'm talking about geographically, seasonally. For example, in our previous experience with Xylella, anything that we did in Italy, in southern Italy, how transferable that is, for example, in the case of Spain, or if we apply to somewhere else. But not even that far away. If we collect images and we calculate indices and build models based on indices from one orchard, and we apply to the orchard which is nearby, is it going to work, or it will not work at all? So I'll give you some examples of why those indices are so much affected by all the aspects I'm talking about. This is a vineyard, for example, and as you can see, and the values of the indices that we will get are totally different depending on whether we are talking about the big pixel that we have here as compared to the size of the pixel, which is a lot better, higher spatial resolution. Why is that? Well, because the whole reflectance here will be calculated based on the different scene components, the sunlit soil component, the shaded soil component, the within vegetation shadow, and the sunlit vegetation. So all these components are used to calculate the index, and will be totally different than if we use, for example, a different spatial resolution image as, like, for example, this other smaller pixel. Through modeling and through data collection over sites where we have different, for example, soil components, we can see here how the relationship between a trait that we use, for example, chlorophyll concentration, and a particular index changes dramatically depending on the soil properties. So that means that the same value of the index would represent, for example, 30 micrograms per square centimeter in one case and more than 80 in another case. So how transferable those indices are. If in one orchard we get a 1.8 as an indicator, for example, of a particular symptom of induced by a pathogen, how can we use it? Because if we go to another site, it will mean something totally different depending on spatial resolution, depending on the background components, depending on the structural effects, depending on the planting grid, for example, and so on. Those relationships, which are empirical relationships between indices and traits that we will use to understand the dynamics of the pathogen-induced stress, will vary depending on the species, depending on the varieties, depending on the phenology, depending on the age, the time, and the date. We collect data in the morning, we come back and collect data in the afternoon, and the indices will be something different, will be in a different range. So the models that we built and we developed for the midday, 11 a.m., for example, local time, will not work over even the same orchard or the same field if we come back 3 hours later. So that's absolutely critical. If we go back to papers that we published many, many years ago, we can see here that PRI, one of the most important indicators that we use and we demonstrated in the case of Xylella, that could be used for the early detection. This is what happens to the PRI index as a function of the amount of chlorophyll concentration or as a function of the changes in the leaf area index. So here we are not even talking about the effects due to the pathogen and the symptoms. Here we're talking about just changes in the photosynthetic pigments or the structure of the canopy. So what is the meaning of a PRI of 0.01? Well, it's absolutely nothing. We don't know how to use it. It will work in the place where it's collected under exactly the same conditions, but cannot be applied to other conditions. The same thing happens to leaf level versus canopy level. This is collecting data in the field at the leaf level. This is the team by Blanca and Juan Antonio, and in the field in different campaigns and while we were flying. And anything that we do at the leaf level, it's very useful, but it cannot be applied directly to the image level. So why is that? Well, because a leaf is not the same as the canopy. At the leaf level, what we put inside of the instrument is just the leaf, is only the leaf. What we see from the images is not leaves, it's the arrangement of leaves, and it's the actual structure and the architecture of the canopy. So answering to those questions, what is the meaning of the indices? Well, there's no physical meaning. We cannot use them other than through empirical relationships. How stable they are? Very unstable. They are useful, but are not robust. They cannot be used from one place to another in time, geographically, or so on. Hard to transfer. So whatever we build, whatever model we build, and we demonstrate that we can use it for detection of stress, it's hard to use it somewhere else. So that is the main reason why I wanted to talk a bit about the modeling. But modeling for me, it's modeling in terms of the rapid transfer. That is the main reason why the whole scientific community working in remote sensing of imaging spectroscopy and quantitative remote sensing of plant traits have developed leaf and canopy models over the course of the time since the 90s, with Prospect, for example, being one of the most widely used leaf level models that take into account the specific absorption coefficients, chlorophyll, carotenoids, anthocyanins, xanthophyll, so on, and water content, dry matter content, all the different pigments and characteristics of the leaves and the canopies are considered in those models. So by doing that, and in the context of several different pathogens and induced diseases, we have used them in order to evaluate early detection versus damage and biotic and abiotic stress indicators, proposing a methodology that is based on what we see here, which is basically a leaf model taking into account the biochemical constituents of the leaves and the arrangement of the leaves and the structure of each of the single leaf elements connected to a canopy model, and together allowing us to go from spectral data collected with multispectral or hyperspectral imaging to the calculation of traits. So we are no longer talking about indices, which are non-dimensional with no units, with no connection with physics, that we don't really understand how they change necessarily, to traits that we can now calculate or estimate in physical units: chlorophyll concentration, anthocyanin, carotenoids, dry matter content, water content, in terms of micrograms per square centimeter. So 30 micrograms per square centimeter of chlorophyll concentration is the same here and over there. And it's the same in my orchard and the orchard nearby. So it's more transferable, and it allows us to make progress on trying to develop models that are more global and more robust. The scheme that we have applied to both verticillium wilt and Xylella fastidiosa can be seen here. It's basically using mechanistic models as the ones that I said before. Those mechanistic models, what they allow us is to quantify the plant traits in terms of photosynthetic and non-photosynthetic pigments and structural indicators. And those are used as input into machine learning models or deep learning models, where we evaluate the importance of each indicator. So we are trying to understand, and we are trying to build the machine learning models not as a black box. We are trying to use the machine learning models to understand the importance of each of those inputs, to understand the physiological processes and to understand the dynamics of the indicators that we use to predict or to detect or to classify trees into different, for example, severity levels. That is how we have gone from using spectral indices in screening methods like the ones you see here into looking at functional traits. We then evaluate what happens not to, for example, a particular index here, but what happens to, for example, to the anthocyanins, or what happens to the carotenoids or to the chlorophyll or to the chlorophyll fluorescence. because that way we would understand better what is the dynamics depending on the species and depending on the pathogens in the context of early detection of diseases. That is also the same methodology that we have applied in the context of abiotic-induced stress. Here, we are not seeing anything related to diseases. Here, we are seeing as water stress increases, how in olive and almond, the different traits change and how those indicators are changing depending on the stress levels. This was critical to improve the assessment and the early detection of diseases in the context of Xylella fastidiosa. Because taking into account the abiotic component, by using or understanding that dynamics of the water stress is the way that we went from around 80-something% and kappas of about 0.6% to more than 90% in the case of olive and almond, and around 92% in the case of olive. So we are using imaging spectroscopy and we are using models to understand the dynamics of the traits, being those traits the ones that characterize the physiological processes happening to the stressed vegetation, being stressed, either biotic or abiotic. And that is how we evaluated for the case of olive and almond, and also across different pathogens, Xylella and verticillium. We could see which of the traits were more important depending on the pathogen and depending on the species. Now the question is, do we need hyperspectral? Is that possible? Can we do that with multispectral data, which is easier to use, easier to collect and to deploy and everything? Well, I think that our few publications on the topic demonstrate that with hyperspectral cameras, we have more spectral bands at specific regions. It's not only having more spectral bands, it's where those bands are located, the very important aspect. So with hyperspectral cameras, we can go in general, both in verticillium and Xylella, we get more than 90% overall accuracies. But if we go to, for example, 12-band multispectral cameras, we go down to 70. And if we go to RGB cameras, then we go very low, not only lower overall accuracy, but very, very low kappa coefficients. And in the case of commercial satellites, we demonstrate how, for example, using Worldview, which is a multispectral high-resolution satellite sensor, we do generally well when we are just trying to map and to classify asymptomatic versus all, all severity levels. This would be the one we get over accuracy and the kappa from hyperspectral and thermal data. This is what we will get, for example, from Worldview 2. This is not much different. We are getting, rather than 90% over accuracy, we get 80-something. So it's reasonable. The problem is when our focus is the early detection. In the case of the early detection, not only the overall accuracy decreases, but more important, the kappa coefficients, meaning that we are going to make much more false positives and false negatives than when we use hyperspectral and thermal data. So final remarks and conclusions of these things I'm talking about. I think that we have made, the whole scientific community has made very good progress in the last around 20 years in hyperspectral and thermal data for biotic-induced stress. I think that we are now successfully getting over accuracies ranging in most cases more than 80 to 90-something% with high kappa coefficients in most cases. I think it's absolutely critical that we use traits for a robust detection, that we shouldn't rely only on indices. We need models to understand the dynamics of the physiology, because that is what first of all, allow us to understand better, But secondly, it's more robust when we try to apply those models to other, for example, orchards or species. It's absolutely critical, particularly for vascular diseases that, I mean, obviously applies to both Xylella and Verticillium, that we need to quantify the abiotic status as a way to improve the detection of the biotic stress. When we take into account the abiotic stress, the water stress in this case, we go from kappas 0.6 to almost 9, from 0.4 to 0.8. So we really improve not only on the overall accuracies, but the kappa coefficients, meaning that we are going to have less number of false positives and false negatives in the detection. I think that we have also demonstrated that with multispectral satellite data, them are useful. So they can be applied, but they are very useful for middle and advanced severities. If we are interested on the very early detection, pre-visual detection, it's where they fail. Why do they fail? Well, it's a combination of how many spectral bands we have, but also the fact that we don't have those that are very critical for the early detection of diseases. About 90%, if not almost everyone in remote sensing providers, just offer RGB or multispectral imagery. I think that is critical if we want to apply and to use these methods worldwide. We really need hyperspectral if the objective is to do good overall accuracies and to perform well with the models that we have developed. And unfortunately, this is not available in many cases. And we are facing these problems in many different projects that we are currently working on. And finally, we sometimes get comments or questions about, can we do that from drones, from airborne, from satellite? At the end, it depends obviously on the scale. It's a matter of a scale and payload, depending on how much we can carry on each of those platforms. For small scale, we can do drones, and we have done it with drones. If we want to have larger scale, then we definitely need piloted aircraft. For very, very large scale, then we need to use satellite. But the number of spectral bands, sensors, and technology available will vary very much, and I'm happy to discuss it if there are questions about it. So just as an acknowledgement, this is the full list of authors that have contributed in different ways to the work that I presented, and those are some of the papers cited in case anyone is interested. And other than that, that's my email address, and anyway, anything else, I'm happy to discuss, and thank you very much again.
Thank you a lot